All right, welcome. We're about to jump into a force that's literally all around us, powering our entire world in ways we barely even think about. We're going to do a super quick, super clear revision of current electricity, from what it is to how we control it. Let's get right into it. You point, you click, and poof, the channel changes. It feels like magic, but it all comes down to the flow of something invisible but incredibly powerful. And that's what we're going to unpack today, the science behind that current. So here's our game plan. We'll start with what flow even means, then look at where it comes from. After that, we'll see how it's all drawn out in circuits, learn how to control it, and then wrap up with why using this energy wisely is so important. First up, the basics.
Okay, let's tackle the biggest question first. When we talk about electricity, what is actually moving? It's time to demystify what a current really is.
The concept is actually way more intuitive than you think. You get what a water current is, right? It's just moving water. Well, an electric current is basically the same thing. It's just the movement of these super tiny charged particles, called electrons, through a material like a wire. That's it, a river of electrons. Now here's a funny thing from history. The early scientists, they guessed that the flow went from the positive side to the negative side. And we still call that conventional current today. You'll see it in a lot of diagrams. The only problem, they were wrong. It wasn't until later that they figured out it's actually the negatively charged electrons doing all the work, flowing from negative to positive. So the real flow is literally backwards from what we call conventional flow. Okay, so if current is a flow, something has to be pushing it, right? This brings us to its sources, which usually give us two different flavors of current, AC and DC. Let's make this super simple. With direct current, or DC, the electrons march steadily in one direction. Think of a calm one-way river. That's what you get from a battery. But with alternating current, or AC, the electrons are doing a frantic dance. They're constantly moving forward and then reversing, back and forth, back and forth. DC is a one-way street. AC is the stuff from your wall socket where the direction flips constantly. So let's zoom in on those DC sources for a minute, the batteries that power pretty much all of our portable gadgets. They're not all created equal, though. They fall into two main camps, primary and secondary cells. And the difference is super easy to remember. A primary cell is a one-and-done deal. Think about the battery in your TV remote. Once it's dead, you throw it away. But a secondary cell, like the one in your phone, is rechargeable. You can plug it in and reverse the chemical reaction to use it again and again. This chart breaks it all down perfectly. The key difference is that chemical reaction in primary cells, it's irreversible. You can't undo it. That's why they're disposable. They're also cheaper and lighter, which makes them perfect for things that don't need a lot of power. Secondary cells, on the other hand, have a reversible reaction, so you can recharge them. This makes them a bit heavier and pricier, but you absolutely need them for power-hungry things like your phone or a car. Okay, so we've got power sources and we've got our devices, but how do we actually connect them? Well, to talk about these connections, we need a common language, and that language is the circuit diagram. It's the blueprint for electricity.
Now, to read these blueprints, you've got to know the symbols. So let's do a quick fire round of the most important ones you're going to see.
First up, the most basic power source, a single cell. Here's a simple trick to remember which side is which. The long line kind of looks like a plus sign that's been stretched out, so that's the positive terminal. The short line is negative, easy. Next, we have an open switch. See that gap? It's just like an open drawbridge on a road. The path is broken, which means no current can get across. And now we close the switch. The drawbridge is down, the path is complete, and we have a perfect unbroken loop. Now the current can flow. This classic symbol with the circle and the X is for a bulb, but it represents a much bigger idea, the load. A load is any part of the circuit that actually uses the electricity to do something useful, like light up, make a sound, or spin a motor. The load is the whole reason we build the circuit. So we know the parts of the circuit, but how do we describe and, more importantly, control what the current actually does? Well, it all comes down to a constant battle between a push and a pushback. First, you've got the push. Its official name is potential difference, but everybody just calls it voltage. Think of it like water pressure in a hose. The more pressure you have, the stronger the water flows. Voltage is that electrical pressure that gets the electrons moving in the first place. That's a great question, right? If there's this force pushing the current forward, is there anything pushing back against it? You bet there is. That pushback is called electrical resistance. As electrons try to flow through a material, they're constantly bumping into and colliding with the atoms inside it. This creates a kind of electrical friction that slows the current down. Everything in a circuit has at least some resistance. So, what affects how much resistance there is? Four main things. First, length. A longer wire is like a longer, more difficult obstacle course, so more resistance. Second, thickness. A thicker wire is like a wider highway with more lanes, making it easier for electrons to get through, so less resistance. Third, the material itself matters a lot. Copper is like a superhighway, rubber is like a total dead end. And finally, temperature. When a material gets hotter, its atoms vibrate more, getting in the way of the electrons and increasing resistance. Okay, so we've got this current, voltage, and resistance. How does this all apply to our daily lives? Well, every single time a current flows through something with resistance, whether it's a tiny wire or a light bulb, some of that energy gets converted into heat. And understanding that is the key to using energy efficiently. This is where making smart choices really pays off. Think about an old-fashioned light bulb. It works by having a super high-resistance filament that gets incredibly hot until it glows. Most of the energy you're paying for becomes wasted heat, not light. LEDs, on the other hand, are designed to create light directly, with way less resistance and heat loss. Choosing energy-efficient appliances is all about picking the ones designed to get the job done with the least amount of wasted energy. And that's the real power here. Understanding the science behind electric current isn't just about passing an exam. It's about understanding how our world works. It gives you the power to make choices that save energy, save money, and help build a much more sustainable future for everyone. So, the question is, how are you going to use what you know?